This video is on optimization and minimizing cost of material. Here I have a storage tank that's in the shape of a right circular cylinder, and the storage tank here has a capacity of 500 gallons. And the cost of construction, the material cost, is going to be $4 per square foot for the material around the tank, and then for the top and the bottom here, the material cost is $10 per square foot. And so the objective for this video is to find for a 500 gallon tank, storage tank, what height and what radius or what dimensions will minimize the cost of construction. And so here's the cylinder. The volume of this cylinder is 500 gallons. And 1 gallon is 0.0133681 cubic foot. And therefore 500 gallons is going to be it will be 66.8403 cubic feet. And so right now I set the radius at 3.6 feet, and therefore the corresponding height has to be 1.64166 feet, because the volume is fixed at 66.8403. And for a cylinder, right circular cylinder, the volume is going to be pi times r squared times the height. And once again, in this case, it's fixed at 66.8403. The material cost, or the surface area of this cylinder, is going to be the lateral area, or the surface area around the cylinder, and then we have the top and the bottom, which is just circles. The area around the cylinder is going to be 2 pi r h, and then of course the top, the bottom, they're circles, so it just be pi r squared plus pi r squared. The material cost for the surface area around the cylinder is $4 per square foot. And so we multiply the 2 pi r h by 4. Material cost for the top and the bottom is $10 per square foot. And so we multiply by 10 and by 10. So this is the cost function right here. And so when the radius is 3.6, the height is 1.64166, and then we can calculate the cost using this cost function right here. So we will get $962.83. And now let's increase the radius. And so we can see that if we increase the radius, the cost of material is going to increase. And what we're looking for is a minimized cost, the smallest cost possible. So let's go the other way. So right now the radius here is 3.6 feet. And right now the radius is 3 feet. And the corresponding cost is $743.73. And so it looks like we can make it smaller. And so it looks like the smallest cost is going to be about $495.05. This one, the radius is 1.6 feet. Let's see if we can make the cost even smaller here. So the radius should be around, for minimum cost, the radius should be around 1.62 feet, and the height should be around 8.1 feet. And the corresponding minimum cost of material will be about $494.97. And so now let's go find the exact radius that will minimize the cost here. And once again, the volume of the cylinder here is going to be pi times r squared h. And in this case, it's going to be 66.8403 cubic feet. And I'm going to call this number here, I'm going to call it B, so I don't have to write it over and over again. And so here, if we're solving for h, then h is going to be B, which is the number 66.8403, is going to be B dividing by pi r squared. The surface area would be the area of the top, the bottom, and then the lateral area. So it's going to be 2 pi r squared plus 2 pi r h. And once again, material cost per square foot is going to be $10 for the top and the bottom. So we're multiplying this circle here by 10, multiply this circle here by 10, and then multiply the lateral area by 4. And then simplify, we get 20 pi r squared plus 8 pi r h. So this will be the cost of material. But right here we have the height of the cylinder is going to be B, which is this number here, dividing by pi r squared. And so in the place of h here, we have B dividing by pi r squared. And so the cost of material, we simplify this term right here. We get 8 times B over R. And so now the cost is a function of the radius, it's a function of R, and we want to minimize the cost here. And so we'll go ahead and take the derivative of cost with respect to R. And here the derivative here is just of R squared is 2R. And so 2r times 20 pi be 40 pi r. And then right here we have 8b over r. And so the derivative of this, we can just rewrite this as 8b times 1 over r. And so we write this as 8b times 1 over r. And then the derivative of 1 over r is just negative 1 over r squared. And so here we will get negative 8b minus ab over r squared. And we want to minimize this cost function here. So we'll set the derivative of c here equal to 0. Multiply each term by r squared. Then we'll get 40 pi times r to the third minus 8b equal to 0. Move this term here to the right and then divide by 40 pi. Then we get r to the third is 8b over 40 pi, which is b over 5 pi. And so the radius is going to be b over the third root of b over 5 pi. But recall that b is just the number, the 500 gallons or the 66.8403 cubic feet. And so we have 66.8403 dividing by 5 pi. And then we use a calculator here and evaluate this expression here. It's going to come out to be 1.6204644 feet. And then the corresponding height is going to be b over pi r squared. And then again, b is 66.8403. And then this expression right here is 1.6204644 for the radius here. And then simplify, we get 8.1023. And so what it means is that to minimize the cost of material, we need to let the radius be 1.62 feet and the height be 8.1023 feet. And then if we look back here at the example, we also saw that the minimum cost, an estimate of it, is when the radius is 1.62 feet and the height is 8.10 feet. But this right here, this would be the exact radius and the exact height that would minimize the cost of material. And that's the end of the video.